Hello, my name is Rob Reynolds. Welcome to Calculus section 4.9. The topic is antiderivatives, and they don't give you many formulas here. The goal is to think about the derivative. How do you undo the derivative? So they're going to give you the derivative, and you're going to try to ask, well, what could I take the derivative? What did they take the derivative of to get that? For example, we know that the derivative, let me try that again. We know the derivative of x squared is 2x. That's simple. Now, I'm going to ask you for the antiderivative of 2x. And we just go backwards and think, oh, well, if I take the derivative of this, then I'll get back to this. That's antiderivative. It's kind of like inverse operations. Instead of addition and subtraction, instead of multiplication and division, instead of exponents, logs. Let's not talk logs. Here we go. We know the derivative of sine is cosine. So if I were to ask for the antiderivative of cosine, you would say sine. Simple enough. The notation for antiderivative is this integral sign. Okay. Actually, at the end of the integral sign, you've got a dx or a du or a dt. And for right now, I'm going to say just do it. I'll explain why that happens later. But notation-wise, I'll just say just do it now. I'll explain in another video why you need this dx, but it's very important. This tells you with what respect you're integrating to. So if you run across another variable that's not in terms of x, the problem gets funky. Then you have this plus c, a constant, and I'm going to explain that in a moment. So that's coming up. And there's something called an indefinite integral and a definite integral. An indefinite just means we're going to go up the plus c route. We don't know what that constant. An indefinite integral means, or excuse me, a definite integral means I have a definite a value and a b. So I'm integrating from a to b over some function in relation to some variable. Oftentimes it's in relation to time if it's a story problem. So if they give you a function and they say, okay, find the area underneath the curve. Well, I actually should have drawn, that's confusing. I'll draw it this way because that's going to be, then I'm going to fill up going this direction. That doesn't make a whole lot of sense to you now, but it will later, from A to B. So I'm moving from A, and I've got all these little rectangles that I'm going to fill up, and you're going to get that in chapter 5. So filling up underneath, and so basically you're going to figure out, oh, integration is area underneath the curve. But for now, all we're doing in chapter 4, the very last section, is thinking, find the antiderivative. In other words, they've already taken the derivative of this thing. I should put this for notation. This is the derivative. So you got to think about, well, what did they have initially in order to get to this? And so we think about the definition of derivative, which if I just put in general form, if I have like x to the n, and I'm taking the derivative of that, then we know that as I go n, dump that out front, n x to the n minus 1. For example, if I'm taking the derivative of, well, let's just do the 3x squared, which will be really confusing because I'm not. But if I was going to take the derivative of that, then of course you'd go 3 times the 2, x to the 2 minus 1. Well, you wouldn't do that. You would just say 6x. But notice that I'm taking this 2 and dumping it out front and then decreasing the exponent. So they've already done that for this problem. So this exponent must have been decreased. In other words, it must have started with a 3. So instead of decreasing, like we do for derivatives, ooh, that's nice. Derivatives mean decrease the exponent. So if you start with a 2, it ends up with a 1. Integral means increase. So actually what's going on here is I'm integrating 3x squared. So I'm going to increase the exponent. And that's nice because integral starts with the letter I, means increase that exponent. And remember, for derivatives, we multiplied by the exponent. Well, all we have to do now is divide. So this 3 kind of just hangs out there. We're going to divide by that 3, and we end up with x cubed. Let's check it. If I take the derivative of x cubed, do I get 3x squared? And the answer is, yeah, that's easy. So I kind of did a little bit maybe more explanation than what I should have. I think this is really section 5.1, but that's how I kind of think about it. Instead of decreasing the exponent, we're going to increase the exponent. So the 2 goes to a 3. And instead of multiplying by the exponent like we did for derivatives, then I divide by the exponent. All right, this one doesn't work quite as nifty because, well, it doesn't follow the power rule. So that's why this lesson is just, can you just think about something that you take the derivative of? What do you take the derivative of? What goes in this box? And out pops a 1 plus x squared. So we're just thinking, and hopefully you have this memorized, because I don't know how you're going to do that if you don't have this thing memorized, but I believe in that box goes what? Tangent inverse. And oh, I forgot something. 6x is the answer for this, but because it was an indefinite integral, they didn't give me an, I should really say 6x plus c. I'm so sorry. Wait, it's not 6x. Oh, right there. X cubed plus c is the, sorry, this was my example. So x cubed plus c should be the answer for part A. For part B, I'm going to do tangent inverse plus c. Again, the only reason why I'm doing plus c is because they just asked for the antiderivative. So the antiderivative just means find the integral of sine. And so I'm thinking, what did you take the derivative of in order to get sine? Well, wait a minute. The derivative of cosine, if I remember correctly, is negative sine. So I can't just put a cosine in there. So how about the opposite of cosine? And then, of course, I have to say plus c. I think those are my answers. Let's just check. There it is for part A, the author's explanation. Yep, there's part B, and there's part C. Hey, I got a couple right. So here's finally the antiderivative definition. We talked about it. P means increase that exponent, and then whatever that number is, divide by it. So whatever that exponent is, divide by it. This doesn't seem like a very important rule now, but it becomes very helpful later. That's that, pop out that constant. That's wonderful. And then you can integrate a plus b as the integral of a plus the integral of b. That's a helpful. Now, I'm going to say this right here and now so we don't get confused. The integral of a plus b, I just told you, was the integral of a plus the integral of b. Yes, do that all day long. But I'm here to tell you, don't fall into a trap and start thinking that the integral of a times b is this. It's not. That's not true. That's a big noper. Don't make up your own rules or assumptions. Later on, we'll learn how to integrate ab, but you can't do it right now. So here's the integral of a plus b plus minus c. So I'll just take the integral of each one. Don't write all that out, but this is kind of what your brain is thinking. Oh, I can pop out the 5 even. X to negative 3 halves. That's that constant rule that I can pop out. I could have popped out this 3. But let's not. Integral means increase it. So the 5 goes to a 6. And then divide by it. So 3, 6. So I get 1/2 x to the 6. Integral, well, this is really an x to the 0. So it becomes, it becomes x to the first and divide by 1. So just plus 2x. That kind of makes sense because the derivative of 2x is back to the 2. Now this one's a little bit harder. So I'm going to increase this guy by 1. And that's like taking negative 3 halves plus 2 halves, which is really x to the negative 1/2. But remember, I have to divide by that as well. So 5 divided by negative 1/2. Now remember, you got this negative out there too. So we got 2 is positive 10. Because instead of dividing by a fraction, you multiply the reciprocal, x to the negative 1/2. So I don't know if you want to leave it like that, that's fine. Let's just say plus c. The next problem, I would go ahead and maybe just simplify. Let's divide each term by x squared. So I'm really taking the integral of 4x to the 17th minus 5x to the negative 10. All right, so let's pop out the 4, increase this to 18, divide by the 18, and come up and reduce. 2/9 x to the 18th. Let's do it again. This is x increase. Now be careful, this is not negative 11. You want to increase it, which means get closer to the higher positive numbers. So how about negative 9? Divide through by negative 9 and end up with a positive 5/9 x to the negative 9 plus c. And for part C, I would probably just multiply it together first. So let's FOIL that up. 2x cubed minus 5x squared plus 2x minus 5, and then integrate. 2/4 x to the 4th minus 5/3 x cubed plus x squared minus 5x. Simplifying, 1/2 x to the 4th minus 5/3 x cubed plus x squared minus 5x plus c. All right, last little thing that, oh, here's some author solutions. I think we got those right. Remember, you can always look at the PDF files posted on Blackboard, and I hope you're following along on the worksheets. The worksheet has a really helpful table 4.9, which I'm going to introduce here in just 30 seconds. But I wanted to introduce this as well. We already know that the integral of well, let me talk here real quick. The derivative of cosine 3x, let's start there, is the sine of 3x times that du. Remember, you kind of have to do a chain rule here. And that du turns out to be the derivative of the inside, which is the 3. So that's where they get 3 sine 3x. So now we're going to take the integral of that, and that's why it's back to just cosine. So that's where they're talking about this a term. So here the a term is 3. So notice, instead of multiplying like we did for derivatives by du, now you divide by the du. So you let a be something, and remember that a term is, well, really a is, you're going to do a let u equal 3x, and then the du, which is the a term, is just 3. So that's why they're dividing by that instead of multiplying by du. So this is that chart that I was talking to you about. And no, you may not use cheat sheets. You have to memorize all of this, but there's a lot of good patterns here because you should already know the left side. So if you know the left side, then we can undo the left side and do the right side. We know the derivative of tangent is secant squared. So if I ask you to integrate secant squared, we get back to tangent. You just have to remember that instead of multiplying by du, we divide by the du, right? So the derivative of secant is secant tangent, and oops, let's do that, is secant tangent. So the integral of secant tangent is just back to secant, and of course we're dividing by that du again. So this one says, what can I take the derivative of to get secant squared? We just talked about it. That's tangent 3x, but instead of multiplying by du, I divide by du, and that's where the 1/3 comes from. The cosine of the integral, let's just not worry about that 1/2 yet. So the integral of cosine is, what can I take the derivative of to get cosine? Of course, that's sine. There's my u. Oh, I should probably say plus c over here because we still have indefinite integrals. And then instead of multiplying by du, I'm going to divide by du. Well, the du is the 1/2. And then instead of dividing by 1/2, so the final answer, it would be 2 sine x over 2. Did anyone see that 1/2? I hope so. The 1/2 of x, because you could write that as 1/2 times x. Instead of multiplying by du, you divide by that, and that's where this goes to a 2. So again, you don't really need the chart, hopefully. If you know the derivatives, we should be able to undo and get the answer. The derivative of e to the x is e to the x. So the integral of e to the x is e to the x. It's a little bit more complicated when you have some chain rule, but instead of multiplying by du, you divide by du. So here's a rule that we haven't looked at in a while. The derivative of b to the x, that's your exponent, is b to the x, just like e to the x was e to the x. But you have to kind of remember, you've got a little extra, that's the L and a B. I don't know if you remember that or not. So then when you integrate b to the x, instead of multiplying by L and a B, that's why they're dividing by the ln of b, because integral is just going to be the inverse of that. I don't know if that makes sense or not. And then we get into these inverses. The derivative of the sine inverse is that 1 over the square root of a. So the integral of 1 over the square root is just that sine inverse. All right, so if you don't have the left side memorized, 4-9 is going to be rough for you, because I'm going to be asking you to integrate e to the u. And the integral of e to the u is e to the u, but instead of multiplying by du, we divide by du. So in this case, the u, so this is just e to the 10x, and then divide by, well, the derivative of 10x is just 1/10, and it's also negative, so negative 1/10, and then I would say plus c. This guy, oh, I would just pop out a 4, and I'm looking at the integral of 1 over the square root of, I'm going to write it as 3 squared minus x squared, so you can see the a term is 3, because that fits my definition, a squared minus x squared. And I know that you know that I take the derivative of sine inverse to get 1 over the square root of. So, I don't know. Let's see if I can bring this to life. The derivative of sine inverse was 1 over the square root of 1 minus x squared. That is really a 1 squared. So now I'm introducing this a term. And if I change that to some letter like a squared, then that's what forms this x over a. And so that's what's happening. I'm letting that a term be 3. So I end up with x over 3 plus c, and I still have that 4 hanging out front. And part C, I recognize that as my tangent inverse formula, where a equals, let me rewrite this as 1 plus 1. Okay. I think I have to back up here. I'm so sorry. I think it is a tangent inverse, but I'm having troubles getting into the right form because I know the derivative. Okay, I think I know what to do. The derivative, I'm trying to get it to be 1 plus that x squared, right? That 16 was messing me up. Can I factor out that 16? So my new problem is the integral of 1 over, I'll throw the dx out there, you can see it, 1 over, I'm going to factor out a 1/16. So it becomes x squared plus 1/16. Then I'll pop out the 1/16, that's the constant rule, and I'll switch this thing around so you can see the a term is right in here. So I'm going to write that as 1/4 squared, ooh, that was a hard problem, plus x squared. So I think the a term is 1/4. And then once we get that, the 1/16 hangs out there. The 1/4, instead of multiplying by 1/4, I'm going to divide by 1/4, so that's why it's a 4. Then the tangent inverse of, and let's see, this guy is usually that x over a, so it's x over the a term, which is 1/4. So I think the final answer is 1/4 tan, oh, that was a hard one. How about 4x plus c? Let's see, I might have messed that up. See if the author agrees. Did I get that one right? Maybe, I don't even remember. Yeah, ooh, there's the one that I was looking for. I think I got that right for B. So I only have time for like one last example. And this is probably the most important thing. They're going to give you the derivative at a certain point. And of course, I've been talking to you about plus C. The reason why, I don't know if I did a good job of talking about why I always say plus C. Maybe I could introduce that really quick too. But to get back to the original function, remember, I just have to integrate that x squared minus 2x, which is what we've been doing the entire video. So integrate means increase and then divide by it. So let's increase this 1 to a 2 and then divide by it, and 2 divided by 2. And then usually we say plus c. Now, you don't really, I've done a terrible job talking about why we say plus c. I should have started with that. But do you agree that if that constant is an 11, if I were to take the derivative of this, I would get back to this, right? But it doesn't really matter if that 11 is a 16 or what that. So that's why we say plus c, because it's just some constant out there, and I should have done that on the first example. So in this case, we just don't know what it is. It's plus c, and it's equal to the function, which we know is some y value. Well, look, they gave me an x, they gave me a y. Because remember, it's always f of x equals y. So I'll let y be the 1/3, and I'll let every x be a 1. And that way, I can solve for c. So 1/3 equals 1/3 minus 1. This is a 1. I'm letting every x be 1 plus c, and I get c equals 1. So then I could write the final equation. The function is 1/3 x cubed minus x squared plus 1. There is one last example, and I will let you, there's the explanation of the c. It doesn't matter where that constant is. Remember, the first derivative is velocity, and the second derivative is acceleration. So if you integrate acceleration, you will get velocity. If you integrate velocity, you'll get the position function, which oftentimes we just let be s at t. So this time we knew that the derivative of a function is its velocity, and we know that the second derivative is acceleration. So now they want to make sure you can go backwards. And you can look at example 6. The video is getting a little bit long. It's worked out here for you. And if you have questions, you're certainly welcome to shoot me an email. I hope this video was helpful.